Hello, my name is Gunnar Epping, and on behalf of my collaborators, those being Peter Quam, Tim Pleskach, and Jerome Busmeyer, I will be presenting our project, Open System Model of Choice and Response Time. This is a pre-recorded presentation for the 2022 meeting of the Society for Mathematical Psychology. The open system model presented here is a random walk process, and this sort of process is commonly used to model people's choice, response time, and preference strength in value-based decision-making tasks. Traditionally, random walk models are formalized as Markov-type processes, such as Markov random walks or diffusion processes, but quantum random walk models have become more prominent over the last 15 years or so. Now, certain qualitative differences accompany the shift from Markov to quantum walks, those being interference effects, where measuring the state of the system alters the subsequent dynamics of the quantum walk, but not the Markov. A quantum random walk predicts a multimodal response time distribution, whereas that predicted by the Markov model is unimodal. And finally, the quantum walk predicts oscillations in mean preference strength over time, whereas the Markov model predicts monotonic increase in mean preference strength. Listed on the right are a few studies that have found evidence for the qualitative aspects that are unique to the quantum model. Moving beyond the qualitative differences, quantitative differences in fit have also been used to compare the two models, and each has been reported to have their respective strengths. The Markov model excels at predicting pairwise choice and response time data, and the quantum model excels at predicting choice and pairwise choice and confidence data, where confidence in an evidence-based decision-making task is analogous to preference strength in a value-based decision-making task. The open system model presented here is a random walk process, and it is formulated in such a way that it combines Markov and quantum random walks in a hybrid fashion, hopefully integrating the advantageous aspects of both models. As a tribute to its potential, the open system model has outperformed both Markov and quantum random walks when fit to preference strength data. And here we extend the model to the absorbing boundary case so that it can be fit to pairwise choice and response time data, which thus far has been most accurately captured by the Markov model. We do note that Fuss and Navarro, 2013, also fit an open system model to pairwise choice and response time data and reported that it produced a slight advantage over the Markov model, but that open system model takes a very different form and is not as general compared to the one presented here. Ignoring random walks for a moment, open system models were first developed to describe how a quantum system interacts with a classical environment, essentially modeling the dynamics of how a pure quantum superposition state decoheres into a classical definite state. The open system random walk model treats the Markov and quantum random walks as two ends of a random walk spectrum, which will be outlined in more detail later in the presentation. Therefore, the open system model can produce mean oscillations in preference strength and a multimodal response time distribution like the quantum model, but does not necessarily have to, as it can also mimic the qualitative aspects of the Markov model. The figure on the right is an example of the predicted response time distributions for the Markov, quantum, and open system models, which demonstrates that the open system can produce a multimodal response time distribution like the quantum model. To collect pairwise choice and response time data that could be used to evaluate the performance of the various models, we recruited 63 participants through Prolific to complete a value-based decision-making task, lasting 7 blocks with 7 trials per block. On each trial, participants were presented with a pair of gift cards, like those displayed on the right. These gift cards varied on 4 dimensions, those being dollar value, restaurant star rating, average price per meal, and distance from home. First, participants were asked to indicate which of the 2 gift cards they prefer. Once the gift card pair was presented, participants were free to respond at any time, and therefore the choice was an internally controlled stopping procedure. After indicating their preferred gift card, the gift card pair continued to be presented for a variable time interval, and then participants were asked to indicate their relative preference between the two gift cards on a scale of -30 to 30. The second response was designed to test another research question, so we did not report the results of the second response in this presentation. Out of the 63 participants, 3 were excluded from the analysis for responding with a relative preference at the ends of the rating scale on over 80% of trials. And as a result, the responses from only 60 out of the 63 participants are included in the reported results. Although all models outlined in this presentation are developed over an arbitrary number of preference states that form an orthonormal basis for each random walk, we use 21 states when fitting the models to data. We chose to use a 21-state random walk because the model fits for worse with fewer states, and adding more states beyond 21 did not improve fits. We did not use more than the necessary number of states needed to attain good fits because of the computational costs of the models. We developed the Markov random walk as a discrete state, continuous time process, where the dynamics are defined using 2 free parameters, those being the diffusion rate, sigma m squared, and the drift rate, um. To map the probability distribution from one time point to another, the Kolmogorov equation is used. For K here is the intensity matrix that is determined by the 2 free parameters. I'm going to skip over obtaining the probabilities for each walk for now, but we'll come back to that later. The quantum random walk is developed in a similar manner to the Markov one, where it is a discrete state, continuous time process, and the dynamics are again defined using 2 free parameters, those being the drift rate, sigma q squared, that's diffusion rate, sigma q squared, and the drift rate, mu q. To map the amplitude distribution from one time point to another, the Schrodinger equation is used. Note, the I in the Schrodinger equation is the imaginary number I, that is the square root of -1. And H here is the Hamiltonian matrix that is determined by the 2 free parameters. First, for the open system model, the state is represented using a density matrix, which is equal to the outer product of the state in the pure quantum model. Now, breaking down this ugly equation up here, the important part is that the left side of the equation is the quantum component, and the right side is the Markov component. The H up here in the quantum component is the Hamiltonian matrix, defined the same way for the pure quantum walk, and the gamma JK here is the element in row J, column K of the intensity matrix, defined the same way as it is for the Markov random walk. And next, this omega here is a weighting parameter, which determines the relative influence of the different components on the open system random walk. When omega is equal to 0, the Markov component disappears and the open system model reduces to the quantum model. Similarly, when omega equals to 1, the quantum component disappears and the open system model reduces to the Markov model. Note, in both quantum and Markov random walks, the diffusion rate has similar interpretations. That is, in the Markov random walk, the diffusion parameter describes the rate at which probability flows out of a preference state into adjacent states. And in the quantum model, the diffusion parameter describes the rate at which amplitude flows out of a preference state and into adjacent states. Given the similar interpretation, we decided to construct 2 different open system models, each making a different assumption regarding the relationship between the diffusion rate of the Markov and quantum components of the system. The first model, which I'll refer to as the equal diffusion open system model, assumes that the amplitude and probabilities flow out of a preference state and into adjacent states at an equal rate. And therefore, it assumes that the diffusion rate in the quantum component is equal to that in the Markov component. Revisiting how probability is computed for each model. In order to convert the amplitude distribution of the quantum model to a probability distribution like that in the Markov model, the magnitude of the amplitudes must be squared. Therefore, it may be the case that in order to equate the diffusion of amplitude with the diffusion of probability, the diffusion rate in the quantum component of the system may be equal to the square root of that in the Markov component. Up to this point, each random walk has been developed as a discrete state, continuous time random walk process with absorbing boundaries. Now, to implement absorbing boundaries, each model repeatedly evolves the state of the system for some fixed amount of time, and then measures the probability that the state is located in one of the two terminal preference states. Each evolution with measurement is referred to as a step in the random walk. Since the number of steps must be discrete, the response time distribution from the discrete state continuous time random walk process is also discrete. Here, we wanted to produce a continuous rather than discrete response time distribution. To do so, we assume that each step in the random walk is exponentially distributed with rate g. Therefore, each step in the random walk occurs according to some continuous distribution rather than at some fixed time interval. And the resulting response time distribution is also described by a continuous distribution rather than a discrete one. In total, the Markov and quantum models both used 4 free parameters, one for the drift rate, another for the diffusion rate, one for the exponential rate mentioned on the last slide, and a non-decision time parameter that encodes the portion of the total response time that did not contribute to the deliberation process. The 2 open system models use 6 free parameters, one being the weighting parameter, drift rates, one for the diffusion rate, one for the exponential rate, and finally one for the non-decision time. Each model is fit to each participant individually using maximum likelihood estimation. To compare the performance of the models, the log likelihood was averaged across the 60 participants for each model and then converted to the chi-squared statistic, which is just -2 times the log likelihood. Since the Markov and quantum random walks are nested models of the open system random walk, we use this chi-square test to evaluate whether we ought to reject the simpler model in favor of the more complex one. The mean g-squared values of each model, the number of free parameters per model, and the results from the model comparison are displayed on the right. And this brings me to our conclusions. We found that when fit to pairwise choice and response time data, the unequal diffusion model offered a better fit compared to that of the equal diffusion model, which supports the notion that amplitude and probability do not diffuse at the same rate. We conclude that we can reject the quantum model in favor of both open system models. Lastly, we conclude that we can reject the Markov model in favor of the unequal diffusion open system model, but not the equal diffusion open system model. We believe this last point is very notable, given that predicting pairwise choice and response time data is one of the biggest strengths of the Markov model. Thank you for listening to my presentation. I look forward to answering any questions you may have about the study.